أسعد الله أوقاتكم حضورنا الكريم. هي الجلسة رقم 2 من اليوم الثاني من المؤتمر. الجلسة هي بمحور الروبوت والتحكم. في عنا حوالي 5 مواضيع بهالمجال هذا. في موضوعين أو 3 مواضيع في مجال الروبوتات. الروبوتات اللينة اللي حيتفضل الدكتور خالد جوهر بإلقائها، والروبوت الجراحي واليد الروبوتية. وفي عندنا موضوعين بمجال التحكم بالأجهزة الطبية، التحكم بالبيس ميكر، والتحكم بكرسي متحرك. نبدأ نبدأ بالموضوع الأول. الموضوع الأول هو Soft-Robotics for Healthcare Technology Applications، اللي هي الروبوتات اللينة في تطبيقات الرعاية الصحية. هي المحاضرة رح يلقيها الدكتور خالد جوهر. ما بعرف إذا الدكتور خالد صار معنا أونلاين. دكتور خالد.
السلام عليكم.
وعليكم السلام ورحمة الله وبركاته. دكتور خالد، نحن أكيد سعيدين بوجودك معنا بهالمحاضرة، فبإمكانك تبدأ مباشرة. معنا 30 دقيقة. تفضل دكتور خالد.
شكرا جزيلا. Can you see my shared screen please?
Okay.
Can you see the shared screen?
بس full screen لو سمحت.
It's a full screen now already.
No, not. It's presentation.
The presentation mode, yes, it's on the presentation
it's
mode now.
F5.
Yes, I did this already.
Yes.
Just. It is on the shared screen now, full presentation. Can you see it now?
Okay, Doctor, you can start.
All right, thank you. Thank you everyone. I think it is still in the morning in Damascus now. Good afternoon or good morning everyone now. It's my pleasure to present for this conference for the third time. So I had the pleasure and the honor to present in the last two venues, 2023 and 2022, and thanks for the organizers. The title will be Soft-Robotics for Healthcare Technology. So I will mainly talk about background of Soft-Robotics, and I will talk about different current and research projects, the current and recent research project in this field. Khaalid Gohar, I'm working now with 2 institutions. So this is my pleasure to be with you now. The outline will be background. So I'll talk about Soft-Robotics, what it means by Soft-Robotics in general. Give you some information. Yes, please. Yes.
أنا بعزم لجنة تنظيمية. في عندك أنت مشكلة بالبرزنتيشن. إذا بتقدر تطفي البرزنتيشن وبتعمل سكرين entire screen presented طفي البرزنتيشن من جوجل ميت.
Right.
انهاء presentation.
Yes, yeah.
هلا حط present whole screen or entire screen.
Do you know from what I can do this one, please?
We don't present the PowerPoint on the entire screen then.
Right. Just maybe. Yes. How now? Does it work now?
You are not sharing your screen.
Right. Just give me a moment, please.
Okay, take your time. Doctor, you can press on present from the domain, the whole screen, touch screen, and then go to PowerPoint and press the font.
Just bear with me, please. Yeah, just because I closed this PowerPoint again, I need to start it again. Yeah. Can you mention it again, please?
Can you present your whole screen?
Yeah, this is like from the.
Present your whole screen.
Yeah, yeah. Right.
You are not present.
Can you see it now?
Yes, then press F5, please.
Just do that. I'm doing this, but like it doesn't work, I think.
Okay, you can go out from the full screen. And
Is it all right now?
you can go out from you can receive your presentation from here.
Yes, maybe. Mm-hmm. Mm-hmm.
أو فيك تعمل هلا كليك تاني بس ما تقدر تعمل بدون الفلس. جرب غير
Right. Mm-hmm.
دكتور بس جرب مشي سلايدات بس نتاكد انه ايه تمام
فيك تبدا محاضرتك على هذا الوضع.
تمام دكتور.
Okay, that's fine. Yeah. Okay, shukran. Okay, so my apology for like the technical issues anyway. So I will start with background. So like mainly I will talk about different literature in the field of software robotics to give you a background on the current focus. I will mention different, probably 4 or 5 different current and recent research projects, mainly in rehabilitation for either lower limb or upper limb. And just to, if we talk about software robotics, actually, mainly the field of software robotics is related to fabrication of robotics. We get used to the robotics which are very traditional, made from rigid material or like rigid metals mainly, or rigid objects. But when it comes to software robotics, mainly we talk about fabrication using soft materials. And the challenge here is if we think about like generating complex motion, we will not be able to have this done by using the traditional robotics systems. One of the, or like some of the very important features of soft robotics, they are very light in terms of weight, and they are very compliant. They have some compliance capability, and we need to have this compliance capability in terms of like complex manipulation and complex grasping of objects, either like this is for human manipulation or maybe for grasping different food ingredients, for example. And mainly they have like low cost in terms of fabrication compared to rigid ones. The picture you can see in front of you now, this is a pneumatically powered soft actuator, and these are like snapshots taken at different time interval. So for example here, the one from the top left corner A, this is at 0 time here, and once we start the pneumatic actuation, the soft robot part will take different configuration, and of course will start some movement. A simple comparison between soft and rigid, or soft and hard robotics, mainly in terms of we are using some flexible or stretchable material, which are mainly reversible characteristics. This is for soft robotics. But when it comes to hard robotics, mainly we are relying on hard material like metal mainly, or plastic, not metal, or maybe just different metals like cast iron, stainless steel, maybe wood, which some of the hard material we can consider. For soft robotics, they are very, very compliance. So mainly when we talk about like man-human interface, exoskeleton devices for augmenting the strength of people, or if we want to do some rehabilitation exercises, we prefer to have soft robotics applied with human body. Hard robotics, they have like, they are complex in manufacturing. Soft robotics have quantum topology, but like the hard robotics on the other way, they have discrete topology. And when we talk about the degrees of freedom, how many manipulation capabilities we can have, definitely the soft robotics can provide indefinite number of degrees of freedom compared to the finite degrees of freedom for soft rigid material. Usually hard robotics are not safe, but like, because we are relying on flexible material, there is adaptivity or adaptive feature of and the tolerance of soft robotics, and this makes them like some advantage when we talk about like work in different environment. Flexibility and stretchable of electronics and power sources. This is very important aspect with related to soft actuators. We rely on conventional electronics, we rely on conventional power source in hard robotics. In terms of bio-inspiration, definitely the soft robotics are highly bio-inspired by nature. Accuracy is low accuracy because soft robotics are suffering from some limitation, like they have low accuracy, low speed and power application, or low speed and force application. Weight and cost are smaller cost, or smaller weight compared to soft or rigid robotics. This is like a chart simplifying the whole thing about what it means by soft robotics as components and what can be the application of it. If we think about a soft robot, we have like an actuator, soft robotic actuator. I'm not talking about traditional motors now, like DC motor, AC motors, or like brushless or brushless motors or whatever. But this is definitely a different configuration. As a soft actuator is one unit. Soft stretchable sensors is the second unit to make a soft robot. We talk about soft and flexible electronics as well, and we talk about like different power supply, different control system, different control central processing unit. So these all 5 components will make what it called a soft robotics. There is a wide range of applications, bio-inspired locomotion, grippers and prosthetic devices are very, very common field of application for soft robotics. Humanoid and wearable robotics as a second one, and definitely medical and assistive robotics has like a big range of applications. And we prefer them, as I mentioned, for human-machine interface. These are examples of soft robotics. I know this is probably could be something strange, but is this a robot? Yeah, because when it comes to the definition of a robot, it's like a programmable machine which can generate motion or can generate or deliver power. Can we deliver power or force from a flexible object like that? Yes, because these are the example of extension and contraction objects. This is like a bending actuator. So if you think about like chambers here, and this is inflatable, pressurized by air or a compressed gas. it will change the configuration, and as a result of it changing the configuration, this will deliver like a high power, can be torque, it can be a force or moment or whatever. If you think about like this is like a twisting or helical actuator, this is like a small motor, by the way, and when you inflate it by compressed air or compressed gas, it will change the configuration, and this means that like you can deliver some sort of moment and torque. There is a wide range of application in grasping, picking, and placing objects. We use them in prosthetics, we use them in food manufacturing for handling food ingredients, and this is an example of a bidirectional or omnidirectional gripper, which is mainly soft gripper. From time to time during my presentation, I will mention about different research projects. I will give you a snapshot for the current focus of number, probably 4 or 5 projects. I will start with soft rigid actuator, and I will talk mainly about the design and fabrication. Okay. As a brief comparison between some of like 3 different type of actuators, like the magpin, muscle, and elastomer, and the textile fabric. Fabric and textile are main focus now in recent research in soft robotics, and mainly because you have lightweight, they are extremely low profiles, but like they can generate huge force, by the way, and force to weight ratio is very important when we talk about textile and fabric. There are different elastomers, there are different magpin like muscles, everyone has its own pros and cons, and this is like probably this slide is giving like some information about like the current state of the art in this field. We are still in the background part of my presentation. As you can see here, like from different pictures, this is like exoskeletons or for augmenting the muscles or like enhancing the motion of a knee joint. So this is like a human knee, and sometimes we need this following knee replacement operations or maybe for knee rehabilitation. And so rather than we use soft or rigid material or rigid robotics which are heavy and consume a lot of power, it comes to here like the soft wearable robotics or soft wearable devices as the common name currently used. They depend on a different configuration. So one of these here, number C, for example, are using inflatable chambers. And once this is inflated or pressurized by a compressed air or a compressed gas, they will change the configuration. So the kinematics change itself, the configuration of the body or the design itself will lead to generating force in terms of either force or torque. And this is why we call it a soft actuator. Soft actuators are commonly used in exoskeletons nowadays for augmenting the upper or lower limb. And one of the things which is maybe still have some limitations here is how we can, what is the power source here? Most common nowadays is a pneumatic as a power source for soft actuators. The trouble with this, the limitation of having pneumatic as a power source, because it does need like a compressor, and there is a lot of research challenges now in terms of can we design, is it feasible, or are we able to design a portable tank or a portable compressor? Not necessarily all the cases. That's why it is still one of the challenges in this research for having a pneumatic or a feasible power source, pneumatic power source, which we can rely on. In this particular slide here, this is like some sort of giving you some idea on some limitation, advantage, and disadvantage of soft rigid actuators. The concept of soft rigid actuator, we have developed it very recently over the last 3 years, and mainly because if we talk about soft actuators, the power or power supplies is very limited because of the flexibility of the material. So we tried to introduce the rigidity component in terms of the actuator. So rather than it is fully rigid or fully soft, we have a hybrid combination or hybrid configuration. So we make use of the flexibility feature in a soft material, but the high strength from rigid material. That's why we have this concept of hybrid soft rigid actuator. And the reason for that is like basically like if we talk about the output force of soft actuators, they still have low power compared to rigid actuators. So we try to have this hybrid design, hybrid configuration between soft and rigid material. That's why we came to the concept of soft rigid actuators. Soft actuators are still suffering from being lower speed compared to rigid actuators. This is one of the aspects the researchers need to look at in the coming few years. They still need a pneumatic circuit and power consumption as well. Just need to one of these areas which we need to consider. This is like some of the literature, recent literature on soft actuators. And from the one in the middle here, this is published in 2014. If you think about like a soft material structure like that with chambers, and when you inflate them with a pressurized air or pressurized gas, it will change the configuration, as you can see in the pressurized or unpressurized shape. And because of the change in the configuration itself, this will lead to delivering a force or torque which can activate a certain object. And definitely we are using them now a lot in rehabilitation of knee rehabilitation mainly. Some of the actuators can be inflated in one certain direction. So this is like mimicking a linear actuator. So rather than you just buy like a hydraulic or pneumatic cylinder, this is like a replacement of something which mimics a linear actuation using a normal linear motor. There's a lot of research happening now in terms of prosthetic devices and mainly using soft rigid actuators. We have a couple of projects if we can design and investigate the design of a small soft actuators to replace the motor part in a human hand. And 3D printing and additive manufacturing here are helping a lot here. So we managed over the last 2 years, almost now, to use the desktop 3D printers to provide or design actuator or soft actuator with high force and precise motion. And when you think about like the configuration of the soft robotics here, we definitely change the stiffness because once you inflate, pressurize it by using a pressurized gas or a pressurized air, you change the stiffness. We talk about now a controllable stiffness or a variable stiffness of the same material. This feature is not available in rigid material because actually when you talk about soft rigid robotics, the stiffness of a certain part in a robot doesn't change the stiffness over time, but like we can control the stiffness as required in a soft robot, and this is one of the things which is a unique feature on soft robotics. Energy efficient is one of the aspects as well because they don't require high power in order to operate them. And this is, I mentioned this before, but like this is probably more details here. Some of the recent literature, so the one in the middle here, you have inflatable actuators, and basically you just inflate it by a pressurized gas, and this will lead to actuation of the knee or augmenting the muscle or doing some rehabilitation exercises. The one here developed in 2022, a different design. So this is like similar, like to have like pillows, and these pillows, once they are inflated, they will be able to activate the knee or augmenting the muscle or do some rehabilitation exercises. This is another project for soft rigid actuator for knee rehabilitation, mainly for post-stroke patients. And we are using this concept of soft rigid actuator, as I mentioned before, because we wanted to have benefit or have the advantage of both the soft features and the rigid features in terms of the high strength of a material. This is like mainly to generate the required motion, force, and knee extension. As I mentioned as well, it has some features for the controllable stiffness and comfortable contact with the human body. This is one of the main important features of soft robotics. There are many applications in soft robotic gloves. So this is like for people who are suffering from stroke, for example. If we think about rehabilitation exercises, like the one on the left here developed in 2015 are totally fabric, by the way, and even like the one in the middle as well, they have fabric based. In 2018, there are some good research happened using additive manufacturing and 3D printed of soft robotic gloves. And the main application for them is rehabilitation or post-stroke rehabilitation. The important thing about robotics or engineering in general, but like I'll focus on soft robotics here, it is like a multidisciplinary team between engineering, medicine, and healthcare. So like it's very important we think about this co-creation and adaptation. And by co-creation, we mean that like as a researcher is not explicitly up to us to think about research, but like co-creation means that like there is an important item here by involving the patient, physiotherapist, and public in the design phase, and this is what we call it co-creation. And because it's very important to consider the end user needs and user acceptance, and this is what's happening in most of our research nowadays. One of the area which I will focus more on now is like for upper limb prosthetics, the soft robotics for upper limb prosthetics. And I will probably talk about more details here about the human hand, because this is one of the main important projects I currently have, is a biomimic human hand. And when we think about the human hand, yani just one of the very unique, complex bodies or part in the human body, and it lies in a gray area, if we can say a gray area actually, between extremely rigid grippers, because we have like the rigidity of the bones and the flexibility of the soft ones. So it is a combination, very, very unique combination between extremely rigid grippers and highly soft ones. So it's not easy to resemble the human hand as like a mechanical gripper. It's not a mechanical gripper. It is not a soft fluid operated inflatable actuator either. It is a combination of both of them. And what makes the human hand very unique is the compliance to complex surface grasp. Easily we can grasp any object, we can grasp any food ingredient, either like rigid or soft ingredients, because we have these compliance features. This is not available in stiff mechanical clamps. Okay? But we still need to have a high force or like a complex surface grasping as well. Okay, so one of the areas which we need to improve with soft grippers is the low precision and degraded force exertion, because mainly due to the excessive elasticity of the material. That's why we came to this concept of soft rigid combination in terms of robotics. Mainly just as like this is like some basic information about the human hand, like a combination of finger, thumb, and palm. And like one of the major projects I currently have now is like this biomimic human hand, or like a soft robotic application for mimicking the human hand. So what we are trying now to do is to replicate as much as possible of the natural feature of the human hand in terms of dexterity, in terms of for grasping, of course, and replicating as much as possible the anatomical structure of the human fingers. This is quite complicated, by the way. It does need some investing a lot in manufacturing techniques. So we currently use different types of additive manufacturing, mainly 3D printing for using the soft material. So we are currently using the Formlab 3D printer in order to replicate the anatomical structure of the human finger. There are many researchers tried over the last few years. For example, people here are considering bio-inspired ligament here, like mainly they start to use bio-inspired ligament in order to mimic as much as possible the human finger. Some others used a mechanical hinge with pivotal insert in order to provide this flexibility, in order to mimic the anatomical feature or structure of the human hand. Others are using like to try to replicate the tendons in the human finger. This is not easy, by the way. This is like totally the one here, for example, by Tian in 2021. This is only 3 years ago. This is like using a soft 3D printing of soft material. And this is basically like using the single material finger designed for with tendon inserted into the bones. And all these trials, people are moving step by step and steady in order to mimic the anatomical structure of the human finger. And the main objective here is to have this compliance features as similar to the human hand. Other researchers as well use the joint capsules.
Khaled?
Yes, please.
We have only 3 minutes.
Okay, so I'm just I'll skip some of the information. So this is like, for example, using joint capsules. Some comparison between the 5 different contribution I mentioned over the last few slides here in terms of the biomimic attributes and functional benefits. The thumb as well has one of the unique features of the thumb is our position motion itself, which makes it signifies a human hand as a gripper, because the human hand is a gripper itself, but it produces a huge range of power grasp and fine manipulation. So like I will skip most of this, I think. This is like different contribution in terms of the inspired thumb. People like using the fixed abduction and extension of the different configuration in the human hand. Bio-inspired features here. This is one of the recent advances in terms of bio-inspired human hand as a prosthetic device for people who lost limb. Palm connectivity, so probably this is like very basic information about like the 3 different arcs in human hand and how we can replicate that in a prosthetic device. The grasping techniques, the grasping feature of the human hand is very unique. So like we can grasp any object as a soft or rigid material, whatever, like within of course the weight limitation and weight capacity of the human hand. Some are using, for example, the bio-inspired palm here, like this particular one in 2016, segmented or actuated palm in 2019. And there are many companies now are using all this research in terms of their commercial products. Again, like a comparison between the different features of the inspired palm, which I mentioned on the previous slide, so my apology, I wasn't able to cover all this in details, but I will send a copy of the presentation for people if they are interested to read all the details here. This is a recent project on soft grasp prosthetic arm for infant people. We did a lot of grasping trials for different cubes, for pens, pencils, for key sets and so on. And we, like the research itself proved, so have success, high level of success in most of these grasping features. This is like another project on the, we call it soft fin ray fingers. This is inspired, by the way, from the fin ray in fish. We developed and designed and developed a soft actuator or a soft gripper for mushroom picking. Actually, this basically was for food manufacturing, for mushroom picking or strawberry picking, because we need to use soft grippers if we wanted to handle some delicate fruits like strawberry, mushrooms, and so on. Yeah, sorry I wasn't able to cover all this, so thanks for the time, and that's all for my presentation. And I'm gonna send a copy of this presentation to the organizer at a later stage for people if they want to read more about that. And you are more than welcome to contact me anytime. Thank you.
Thank you, Dr. Khaled. We will see if there is any questions. Yes, please.
Thank you very much to Dr. Jawhar. I'd like to ask you about soft technology related to uses in disabled people. I want to ask I want to ask about the technology. Is there a human central nervous system control in this algorithm, or how, for example, we have sudden actions and we need special technology to control it. And on the other hand, I want to ask you if there is insurance related to this machine for disabled people or who needs this technology. And I hope to respond soon. Thank you very much.
So thanks for the question. Like with these two parts of the question, actually, there are different technology complexity in terms of design of and the development of prosthetic devices for people. One of the main elements which will make the choice here is the cost of the device. Prosthetic devices are very, very expensive, and it depends on depending on the type of technology. And when you talk about like neuro signals here, so you have range of prosthetic hand, for example, range between maybe a couple of £1,000 to maybe like £50,000, for example. And this will depend on the technology and the know-how for using them. I think from my point of view, I believe prosthetic hands or prosthetic devices should be available and affordable for people. So I don't tend to use complicated technology for prosthetic devices, because when you think about like maybe developed countries and like low-income nations, having this affordability feature is very, very key part here in terms of the design itself. The second part about the insurance, many devices has been designed and developed are still in the lab basis in terms of lab trials. To go for medical regulations, depending on the regions. Some regions is very complicated to have regulation for a medical device. That's why some of the devices or robotics are commercialized as a mechanical equipment in order to bypass this particular part about the medical regulation and the insurance. I think insurance companies will be very, very reluctant to insure these devices, from my point of view, because of the risk. Yeah. And hopefully this answers your question.
Okay. Thank you, Dr. Khalid, for your valuable contribution. Thank you.
My pleasure. Thank you.